Welcome to lecture 12. Today we will talk about resonant circuits. And what that is, you will see in a minute. Let's begin with a so-called series resonant circuit. Here we have a series connection of a resistor, an inductor and a capacitor. And we know the values of the given elements, and we also know the absolute value of the voltage source. And our variable here is the angular frequency. That means we have a sinusoidal voltage source and we can vary the frequency of the sinus there. And obviously, when we have a voltage source and a passive load connected to it, there will be a current. And this current can be calculated with Ohm's law, and the total impedance of our series circuit is just the sum of the single impedances. Okay, and now let's have a look at our circuit. We are free to select an angular frequency omega. And if we take a very low value, lower, and until omega is 0, that means that we have a DC voltage source. And when we have a DC voltage source, the capacitor behaves like an open circuit. And that means that the absolute value of the current is 0. Okay, and now let's increase the frequency, and let's increase it. And if we do so for very high frequencies, the inductor behaves like an open circuit. And that means for very high frequencies, again, our current will become 0. Okay, and now I have two questions. The first one, when we have no current for DC and no current for very high frequencies, what will the maximum value of the current be? In the middle somewhere. And the next question is, which will be the angular frequency where the current has its maximum value. Okay, let's have a look. So we have our circuit and we have an equation for the current. And we want to maximize the absolute value of this current, and the current will have its maximum value when the impedance has its minimum value, because it's in the denominator of the equation. Okay, let's have a look at the impedance. We have a constant real part, just the resistor value, and we can't change anything about that. But the imaginary part is frequency dependent, and we subtract two terms from each other, and that means that the imaginary part could become 0. That means our impedance becomes minimal when the imaginary part of it becomes 0. Okay, so that means that the expression in the brackets have to be 0, and here I call the angular frequency omega 0. That is just a name for this situation that we have the maximum possible current in our circuit. Okay, so we can solve this equation. And you see, we can solve it for omega 0. And in the end, we find this expression. And this is the angular frequency where we have the maximum current, and we call it resonant angular frequency. And if we want to describe it with real frequencies, you know you come from omega to f with this term 1 divided by 2 pi. I prepared a small simulation, and therefore I have values for our elements, and the absolute value of the voltage is 1 volt. And now I will draw the absolute value of the current independently of the frequency. And have a look, it looks like this here. As we said, when the frequency becomes 0, then no current flows, and you can guess if we have very high frequencies, then the current will be 0 again. And in the middle there is a maximum value for the current. And we just found out the angular frequency can be calculated like this. With our number values given here, this leads us to this angular frequency. And if we want to express this with the frequency in hertz, we have to divide the result by 2 pi, and this leads to a frequency of 1300 hertz. And you see it here also in our picture. I want to show you the same thing again, but this time have a look the y-axis of the diagram where I plot the current has a logarithmic scale now. And you remember we can calculate our resonance frequency like this, and with the given values of L and C we will have again our resonant frequency here. And the curve you've already seen looks in the logarithmic scale like this. Okay, and you see it fits. The maximum value of the current is where the resonant frequency is. Okay, but have a look at our circuit. We have R, L and C there. And our resonance frequency is only dependent from L and C. But I'm sure the resistor will have an influence to it. And therefore I try it with another value. This time I use a resistor with 100 ohm. Let's have a look. Interesting. The maximum value of the current increase. Okay, that is no wonder, because at resonance frequency this circuit just behaves like the resistor, because the imaginary part of the impedance was 0. So it's clear when we have a constant voltage and a smaller resistor that the current increases. Let's have a look what happens when we have a 10 ohm resistor. Then the curve looks like this. Okay, there are two interesting things here. The first one is the current increases with decreasing resistor values. Okay, that is not that surprise. But what's more interesting is that the curve of our current gets tighter around the resonance frequency. Let's have a look on that. Here I've drawn the diagram with a linear scale again. And we already calculated our resonance frequency. And we know that at the resonance frequency we have the maximum current. And now let's think about the power consumption of the circuit. In our resistor, the power consumption will be the maximum current square times R. And now let's just calculate which current we need to have half of this maximum power consumption. And It's quite easy because we take the square out of the current. It means that we have to decrease the current by the factor square root of 2 to get half of the power. Okay, we can draw this current here in our diagram, and now there is a definition for these two frequencies. These frequencies we call the corner frequencies. And between these two corner frequencies, we will have the maximum power consumption of our circuit. That is where the resonance frequency is. And between these two frequencies is the maximum power and at least half of the maximum power. And outside of this frequency band, the power consumption will be lower than half of the maximum power. So we call them corner frequencies, as I said, and the width between these two frequencies we call bandwidth. And then there is a third definition, the quality, and the quality is defined by the resonance frequency divided by the bandwidth. So resonance circuit has a better quality when the bandwidth is smaller. So we can find the bandwidth if we have our diagram. But now I will show you how we can calculate the bandwidth. The way to get the final equation may be a bit difficult, but in the end we will have a very simple equation for that. Okay, so here is our circuit and the equation for our current. And we know that if we have resonance frequency, our impedance just behaves like the resistor, and therefore the maximum value of our current can be calculated like this. And now we want to find the values for omega, where we have the maximum value divided by the square root of 2. So what we need is our equation again, and we want to have a look at the absolute values, and therefore we take the absolute value of our impedance. And now let's think. The absolute value of the impedance has to be bigger than R and by the factor square root of 2. How could we have that? So let's draw a phasor diagram of the impedances. If R is this here, and we want to find an impedance which is square root of 2 times R, then we could find it either here, when we have an angle of minus 45 degrees, then the imaginary part is as big as the real part, and from Pythagoras we know that the absolute value here would be square root of 2 times R. And there is another solution. We have two corner frequencies. We could also have this impedance here with a positive phase angle. Okay, let's have a look how we can get them. Let's start with a phasor diagram and we draw the impedance. We start with R. And then we have in series connected the inductance there, and it has j omega L. And if we have low frequencies, then the part of the capacitor will be bigger, because there the angular frequency is in the denominator. And for small values, this part here will be bigger than the part of the inductance. And therefore you see we can get an impedance which absolute value is square root 2 bigger than the value of R. And this means that R has to be the negative value of the imaginary part. For the other corner frequency, we have the same thought. We have our impedance of R, but this time the frequency is bigger, and that means that j omega L becomes bigger, and 1 divided by j omega C is smaller now. And therefore you see we can find values that we have this positive phase angle. And here our resistor value has to be the positive imaginary part. Okay, let's calculate it. We know that for our first corner frequency, R has to be as big as the negative imaginary part. And therefore, we can solve this equation for omega 1, and then we know the corner angular frequency. So I write the equation the other way around, and now I multiply with omega 1. I bring the R to the other side and I divide by L. And now I can use my PQ equation, and it leads to this here. From a mathematical point of view, you would say, hey, there has to be a plus minus in front of the square root. Yeah, you're right, but if we had a minus there, then we would calculate a negative angular frequency, and it has to be positive, and therefore I just write the plus here. Okay, the next corner frequency has the condition that the resistor value has to be as big as the positive imaginary part. And now I do the same. I bring the omega parts to the left side and I solve for omega 2. It looks like this. And again, I can use my PQ equation, and it leads to this here. Let's start a new sheet. So we have these two results, and we wanted to calculate the bandwidth. And therefore, the bandwidth is, to get real frequencies, 1 divided by 2 pi, and then the difference between the two angular frequencies we just got here. So that means we can write it like this. It still looks horrible, but have a look. We have a minus sign between our two terms. And that means that we get rid of these ugly square root expressions, and then we have this term r divided by 2l. Minus minus is plus r divided by 2l, so that means in our big brackets we just have r divided by l, and therefore our bandwidth can be calculated like this. And for you, it's enough that you now know that you can calculate the bandwidth with that equation. But I didn't want to let it pop up like a miracle and just say, and you can calculate it like this. Now you have an idea how you can come to this equation. If we have a series resonance circuit, then obviously we could have a parallel resonance circuit too. Again, we know the values of our elements here, and we can vary our omega. And again, we want to find the current here, independency of omega. Okay, we can calculate the current according to Ohm's law. with voltage times the admittance of our load circuit. And the admittance of a parallel connection is just the sum of the single admittances. Okay, let's have a look at our circuit. When we have a DC voltage source there, then our inductor behaves like a short circuit. And that means if we had a constant DC voltage there, then our current would be infinite high. And if we have very high frequencies, then our capacitor behaves like a short circuit. And again, that would mean that at very high frequencies, our current would be infinite high. Okay, and this time our questions are, what is the minimum value of I then? And at which angular frequency do we have our minimum value of I? Okay, so we are looking for this current. And we know that we can calculate it like this. And we want the current to be minimal. And the current becomes minimal if the admittance becomes minimal. And how could we make that? The imaginary part could be 0 again. And that means that the part in brackets has to be 0, and therefore we can write it like this and solve it for the angular frequency, and we find out that the resonant angular frequency is again 1 divided by the square root of LC. And that means that the resonant frequency expressed in Hertz is 1 divided by 2 pi square root of LC as before, but this time the bandwidth is 1 divided by 2 pi RC. And just believe me this time, I don't want to calculate 2 or 3 pages again. With the same values as we had before, I made another simulation, and the current here looks like this. And again, we know the resonant angular frequency is this here. With our number values, it just leads to the same value as before, and we can calculate the resonant frequency value, and this is again 1300 Hertz. So, as before. At this point of the lecture, many students think, cool, when I have any circuit with L and C, then it's a resonant circuit. That is right. But then they say, and the resonance frequency is 1 divided by 2 pi square root of LC. That is not always correct. That is correct if we have a pure series resonance circuit or a pure parallel resonance circuit. And in the end of this lecture, I will show you an example where we will get another result, just to give you the impression how to deal with resonance circuits. Okay, so we have the circuit and the elements are given. And now we should find the angular resonant frequency omega 0. And our condition for that is always the same. We want the imaginary part of our impedance to be 0. You may say now, hey, wait, at the parallel resonant circuit we had the admittance. Yeah, that's right. But if our impedance or our admittance has an imaginary part, which is 0, then the impedance is just a real number, so just a resistor value, and the inverse of that would also be a real value, so just the conductance value, but the imaginary part is 0 in both cases. Okay, so this time it's more convenient to deal with the impedance because we have this series connection of two elements. And we can express it like this: the impedance of the inductor plus the impedance of the parallel connection. And this time I used the equation that it's the inverse of the sum of the admittances. Okay, and now I want to split this expression for real part and imaginary part. But to do so, the j's which indicate the imaginary part has to be in the counter, and there is a j in the denominator. How can we get rid of that? We can get rid of that with a trick. I expand the fraction with the conjugate complex of the denominator. The conjugate complex of a complex number is the same complex number, but the imaginary part flips its algebraic sign. Okay, so we have a new counter and there is a complex number and we have a denominator and it looks like this. And now remember the third binomial equation. A plus b times a minus b equals a square minus b square. And here in our case, the result will be 1 divided by r square minus j omega c square. So in the negative part is a j square, that becomes a minus 1, and therefore our denominator looks like this. It becomes pure real, and we have 1 divided by r square plus omega c square, and the j disappears because we have j square. That becomes minus 1, and with that minus 1 our negative sign from the third binomial equation becomes plus. Okay, and this term can be separated into real part and imaginary part. Let's start a new side. And now we want the imaginary part to be 0. Okay, there is omega 0 at 3 positions and we want to solve this for omega 0. But we are lucky, we can just shorten here these two omega 0s, and therefore our expression can be solved like this, and therefore we can solve more, and this leads to an omega 0 which looks like this. And I don't like this double fraction, so I divide the two things under the square root there by c square, and it leads to this expression. So this was an example, and an exam task look exactly like this. In an exam you might get a circuit consisting out of R, L and C, and you should find the resonance frequency, and it's always the same. Find the total impedance or the total admittance, what is more convenient in that case, and then solve the expression for the impedance for real and imaginary part and set the imaginary part to 0. And then solve for omega. And that is the resonant angular frequency.